So I did the chemistry of hydrogen cells. So what is a hydrogen cell? Its fuel cells operate as a normal battery. However, unlike batteries, they don't have to be recharged, sort of. So as long as they are supplied with the fuel needed, the fuel cell will continue working, basically like an infinite fuel source. There are many different classifications of fuel cells. This all depends on things such as what types of reactions occur in the cell, the types of fuel required, and the right ideal temperatures. So some operate best at like 60 degrees Fahrenheit, some operate at 80 degrees Fahrenheit. The different type of fuel cells are polymer electrolyte membrane fuel cells, which we'll be focusing on today. And then there's also direct methanol fuel cells, alkaline fuel cells, phosphoric acid fuel cells, molten carbonate fuel cells, and solid oxide fuel cells, and there's also reversible fuel cells. So how does it work? For this demonstration, like I said, we'll be focusing on the polymer electrolyte membrane fuel cells, also known as PEM cells. PEM cells run off of hydrogen, which is provided from a tank or a reformer. A reformer is a fuel source which will constantly produce hydrogen, allowing the PEM cell to have an infinite fuel source. What makes a PEM cell? So right here, you can see I've got a diagram that talks about the different layers, which we'll get more into in the next slides. A PEM cell is made up of only a few things, making it a simple but effective fuel source. PEM cells use solid polymer as an electrolyte and porous carbon electrodes. In order for the PEM cell to produce electricity, all it needs is hydrogen, oxygen, and from the air and water. So this is the chemistry behind a PEM cell. First off, we're going to talk about the membrane electrode assembly. So that's the inside of the PEM cell. The polymer electrolyte membrane looks just like your ordinary kitchen wrap you'd find in your house. However, the polymer electrolyte membrane has been especially treated, making it conduct only positive charged ions while blocking electrons. This is key to the fuel cell due to the fact how it only lets necessary ions through while blocking everything else out that would disrupt the chemical reaction. The next part is the catalyst layers. These layers are placed on either side of the membrane. These layers include a nanometer-sized particles of platinum dispersed on a high surface area carbon support. This layer is mixed with ion-conducting polymer and is then placed between the membrane and the GDL's gas diffusion layers. The ion-conducting polymer allows protons to travel through the many layers. The last part of this assembly is the gas diffusion layers. These layers are placed outside of the catalyst layers. They allow reactants and bring them into the catalyst layers, while also removing product water. Gases rapidly build up on these layers, which ensures that there is a coat of high surface area carbon mixed with layers which ensures that there is no excessive water buildup in the membrane. Commonly, these layers have a thin coat of high surface area carbon mixed with PTFE called the microscopic layer. The microporous layer adjusts the balance between water retention. This is needed to maintain the conductivity of the membrane. This also improves water release, which is to keep the pores open so hydrogen and oxygen can diffuse into electrolytes. And this is my demonstration. As you can see, this side is the hydrogen, this side is the oxygen. The fuel cell is back here. Basically, the hydrogen builds up into here, the oxygen builds up in here underneath the two cones, powering this fan for a decent amount of time until it runs out. This experiment didn't use a reformer, meaning that it didn't make that infinite fuel source, more as a temporary fuel source, as you'll start to see the fan starts to die. And lastly, this is the hardware of the PEM cell. So it uses bipolar plates, which allow us to stack multiple MEAs due to the fact that they only produce about under 1 volt under normal operating conditions. With stacking these, it allows us to produce more than the 1 volt, allowing us to power things much larger than what you saw today as the fan. which can even power up to car batteries, things such as Teslas and whatnot. Lastly, with each MEA being sandwiched between two bipolar plates, rubber gaskets must be used in order to make sure that it's a tight seal. That way no gases escape, ultimately causing the reaction to fail. And these are my sources.